Hey everyone, and welcome. Today, we're going to try and crack the code on randomness. We're going to explore the mathematical language that helps us find order in what looks like chaos and predict patterns in the unpredictable. So let's just dive right in. I mean, this is the big question, right? Think about it. Whether it's the simple flip of a coin, the incredibly complex inheritance of a genetic trait, or even something like the number of calls a support center gets in an hour, our world is just filled with these random events. So how do we make sense of it all? How do we get from just pure chance to something we can actually calculate?
Well, the answer is we need a framework. We need a set of tools. And it all begins by learning the basic vocabulary, the language that lets us translate real-world randomness into numbers we can actually work with. And the single most important word in that new language, the absolute cornerstone, is the random variable. Seriously, this is the foundational building block for everything else we're going to talk about. It's the concept that lets us finally start doing the math.
So what is it? Honestly, the best way to think about a random variable is like a translator. It takes a real-world outcome, something like a coin landing on heads, and it translates it into a number, like 1. If it lands on tails, maybe that's 0. And just like that, instead of words, we have numbers. And that's where the magic starts. Okay, so once we start turning these outcomes into numbers, you pretty quickly realize that these numbers live in two very different worlds. And understanding this difference is absolutely crucial for picking the right statistical tool for the job. So on one hand, you've got discrete variables. These are values you can count, like the number of heads in 3 coin flips. You can get 0, 1, 2, or 3. But you can't get 2.5 heads, right? It's impossible. On the other hand, we have continuous variables. These can take any value within a given range. Think about a person's height. It could be 175 centimeters. Sure, but it could also be 175.1 or 175.11. The possibilities are basically infinite. And this visual just perfectly nails the difference. For that discrete, countable data on the left, we use a bar chart. Each bar represents the exact probability of a specific outcome. But for the continuous data on the right, we have to use a smooth curve. See, you can't really ask about the probability of being exactly 175.111 centimeters tall. Instead, you ask about the probability of being within a range of heights, and that probability is the area under the curve for that specific range. All right, so let's dive into that first world, the world of countable outcomes. We're going to look at a few common recipes, or distributions, that statisticians use all the time to model these kinds of discrete events. These are the go-to tools for counting things. And first up, we have the absolute workhorse, the binomial distribution. You use this when you have a set, fixed number of trials, like say you're going to flip a coin 15 times. Each of those flips is totally independent. Each one has only 2 outcomes, heads or tails, and the probability of getting a head is the exact same on every single flip. And this isn't just for coins, you know? It applies directly to really complex fields like genetics. The logic is the same. A fixed number of trials, 5 children, 2 outcomes for each, healthy or not. A constant probability. And if we know that each child has a 75% chance of being healthy, the binomial distribution can calculate the precise odds of having exactly 4 healthy children. It takes this deeply personal question and gives us a concrete numerical answer. Okay, so let's build on that. Our next distribution is called the hypergeometric. And this quote just perfectly sums up how it relates to the binomial. It's for very similar situations, but with one critical game-changing twist. You're sampling without replacement. Just picture it. You have a big urn with 100 balls, and 20 of them are white. On your first draw, your odds are simple, right? 20 out of 100. But, and this is the key, if you don't put that ball back, what happens? Suddenly, the odds have changed for the next draw. This exact same logic is so important in genomics, where scientists draw genes from a finite pool to see if a certain function is showing up more than you'd expect by chance. Okay, our last stop in the discrete world is the Poisson distribution, and this one has a very cool, very specific job. It's our go-to for modeling rare events. You use it when you're counting how many times something happens over a certain amount of time or space, especially when that thing doesn't happen very often. Just look at that number. It's tiny. It's basically 0, right? Well, this is the calculated probability of a human having 12 or more spontaneous, harmful genetic mutations, assuming the average is just over 1. What's amazing is that the Poisson distribution is what lets us calculate the odds of these incredibly rare, but biologically super important events. All right, so we're leaving the world of distinct, countable bars behind. Let's step into the smooth, flowing world of continuous curves. We're talking about continuous data now, and there is one distribution that is king here, the normal distribution. You probably know it as the bell curve. And there's a reason people call this the most important distribution in all of statistics. So many things in nature, human height, blood pressure, even tiny measurement errors in a lab, they all tend to clump around an average, with fewer and fewer results way out at the extremes. This symmetric bell shape is so common, it's normal.
But why? Why does this bell shape show up everywhere? The answer, honestly, is one of the most beautiful and kind of magical ideas in all of stats, the central limit theorem. Look what's happening here. At the top, you've got these populations with all sorts of wacky shapes, right? But watch what happens as you start taking bigger and bigger samples, and you plot the average of each sample. It's wild. The distribution of those averages just magically starts to form that perfect bell curve. Every single time. It doesn't even matter what you started with.
Phew. Okay, that was a lot, I know. We've gone from counting successes to the universal bell curve. So let's wrap this up with a quick guide to kind of put it all in one place for you and make sure it sticks. Think of this as your quick and dirty cheat sheet. Binomial, that's for your fixed number of yes-no trials, like flipping a coin. Hypergeometric, similar idea, but it's for when you're grabbing from a small group and not putting things back. Poisson, that's your guy for counting rare events over time or space. And normal, that's the classic bell curve for all those continuous measurements, like height and weight. And that brings us to our final thoughts. You now have the basic vocabulary to describe randomness. It's like having a new lens to see the world through. So the next time you see a statistic, or hear a probability, or just notice a pattern out in the wild, maybe you'll recognize the blueprint hiding just underneath the surface. What new patterns are you going to see?